Welcome to this pre-class video on triacylglycerols. Well, triacylglycerols, aka triglycerides, aka tags, is the way that animals store fat. So if you look at fat cells called adipocytes, they are full of triacylglycerol molecules. Also, just a fun fact, the most abundant lipid in one's diet are triacylglycerols. So, very important molecule. Well, what is a tag? Well, you have the base of a tag is glycerol. Now, glycerol is what we call a triol. Here's glycerol. It's a triol because it's a, if you want to say it this way, a trialcohol. It's got 3 hydroxyl groups. Okay? And to that, you react 3 fatty acids. And now this is just my cartoon for a fatty acid. It's a carboxylic acid plus its long non-polar tail. When you bring these two together, then you get this. And so you have the kind of the foundation, or the base is the glycerol molecule. We also know from this class that when you react a carboxylic acid with an alcohol, you get an ester. So this is also a triester molecule. And you can see R C double bond O R here if you look close enough. So there we are. I'm being very non-specific about the I'm not being specific about the non-polar tail because it can be a variety of things. We may even show this in even more shorthand notation, where we just draw like a flattened circle for the glycerol and we draw it like that. There we go. Again, it shows the triester nature of the molecule. So, where would you might encounter a triacylglycerol? Well, most of the oils and lard type products that we use on a daily basis, you may cook with them or use them for other purposes, are really mixtures of triacylglycerols. For example, peanut oil. You go to the Walmart. Look at this. I got the Great Value brand here. If you go to Walmart and pick up some peanut oil to be frying something in, then that in here, right in here, really is a mixture of tags. And basically, the different types of oils you can buy, which there are numerous these days, have a different combination of fatty acids that are used to make the tag molecules. Now, for example, peanut oil is composed, the fatty acids used to make the tag that we just saw, 19% of them in peanut oil are saturated fatty acids. Saturated fatty acids. And I'm not going to give you the full rundown. I'm just giving you 2 important notes for peanut oil. 48% are of the fatty acids. 19% of the fatty acids are saturated in the triacylglycerol molecules in peanut oil. 48 are, oh look at that, our old friend MUFA's mono unsaturated fatty acids. So what you need to get in your mind is oils and fats typically that we encounter on a daily basis are typically mixtures of triacylglycerols with different percentages of fatty acids. Alright, well, what else do we need to know about triacylglycerols before class today? Well, I've kind of drawn a cartoon of a triacylglycerol, again with the glycerol as a flattened circle, and then we see the triester nature of the molecule. Again, this is a tag, just so we're clear. And then we see the 3 fatty acids. Here, look at the different, again, this is to illustrate in relation to what we just talked about with peanut oil. you can have different combinations of fatty acids in a tag. This fatty acid, again, this is a cartoon. I'm just using squiggly lines as part of the nonpolar tail. I don't want to be specific about how many carbons right now. But what I have been specific about is whether or not there's a double bond or not. So this fatty acid in this position of the tag molecule is a MUFA. It's a monounsaturated fatty acid connected to glycerol. This one is a saturated fatty acid. There are no double bonds. And this one is a PUFA, a polyunsaturated fatty acid used to make the triacylglycerol. Now, one of the things that we're going to really emphasize in class is that if you look at food labels, you're going to see the term a lot. Partially hydrogenated vegetable oil. So these oils can come from animal sources, it can come from vegetable, plant type sources. But what does this mean, partially hydrogenated vegetable oil? Well, that means that the tags of the food have been reacted with hydrogen, with palladium. And we've seen this before, briefly in this class. And so what this does is that every time you hydrogenate, let me just say it this way, and we're going to get into this in greater detail in class, each mole of the H2, and this is just the metal catalyst platinum, each mole of H2 platinum removes a carbon-carbon double bond. You basically, ladies and gentlemen, convert the alkene to an alkane. So you are getting greater saturation. You're producing a molecule that is more saturated because you're taking away the double bonds. And we know adding double bonds is greater unsaturation. Now, in class, so this is more, let me write it like this, more saturation. I can't seem to write more very well. This is going to affect the properties of the tag. And again, we typically, or the food companies typically do partial hydrogenation. You don't want to remove all of the double bonds. You just want to remove a certain number of them. You don't want to remove all of them. And when you hydrogenate a tag molecule, you change its properties in terms of when you hydrogenate and you get more saturated, you make it more solid-like. The tag molecule becomes more solid because you're removing these double bonds. We've learned previously that adding double bonds to a fatty acid tends to lower its melting point. So, partial hydrogenation leads to a more solid-like consistency for a tag molecule. All right. We'll get into more of this in terms of why do we want to do this, etc. in class. Hope this video was helpful.